Hello, welcome back to Organic Chemistry. My name is Todd Rothman. In this video, we're going to go over formal charge. Now, at this point, we have a review from Gen Chem on atoms, on bonding, on how to fill electrons in, electron configurations. And now it's time for us to start moving towards drawing Lewis structures. But before we do that, we have to remember how to figure out the formal charge of an atom at any given point in time. Okay? Now remember, the charge of an atom changes because the number of electrons are constantly changing around that atom. The nucleus is the same, so it's always the same number of protons. It's just a question of the electrons. So let's get started by taking a look at the basic rules for formal charge. So formal charge, there's a typo here, but that's fine. Since electrons, right? Since electrons are variable, we have to kind of keep track of how many electrons are around an atom at any given point in time. And what happens here is that the electrons will sometimes be added to an atom, and that'll make it more negative. Or other times, electrons might leave an atom, and that would make it more positive. So we have to figure out what the charge is, right? And that's formal charge. So there are many ways that you can do this, but I find personally that this is the easiest way I like to do it. Now, let me just tell you, whichever way you choose to do formal charge, just remember that this is something that you're going to do very frequently, and it's not something that you want to spend too much time thinking about. So the traditional formula for formal charge just takes a little bit more time to think through it because you have to unravel the formula, whereas this is a quick and easy way to do it, okay? But again, you might have another way, and this is just the way I like to do it. So what I do is I take the valence number, and that I usually know for the common atoms, like carbon is 4, nitrogen's 5, and so on. Or at least if you know carbon, you can work your way around. So you know the valence number, or look at the periodic table, look at the group number, and you subtract it by the electrons that are owned by that atom. Now, what do I mean by that? Now, recall from the previous video that when you have a covalent bond, that each atom owns one electron and they come together and they share their electrons, but they only own one electron. So whenever you see a bond, whether it's a single bond or a double bond or a triple bond, even though each of those bonds is 2 electrons, each atom only owns one of them, okay? So the very quick way to do it is you take the valence number and you subtract it by the electrons owned. And a way to figure that out is whenever you see a bond or a stick, count it once, because there's 2 electrons in there, but only one is owned by the atom. So sticks you count once, and any kind of electron that's on an atom, like a lone pair or a radical, that is owned by the atom, right? So you count sticks and dots. That's the basic way to do it. So you take your valence number, subtract it by the sticks and dots, and that's it. So I'll show you what I mean right now. Now, here's an example, and by the way, so here's our periodic table. I just want to remind you that the valence number is the group number, right? So H is 1, beryllium is 2, boron is 3, carbon 4, and so on. So we're going to look at the group number in just a moment. Now, in our example down below, let's figure out everyone. Well, first off, hydrogen's very simple. Hydrogens want one bond, and that's all they can have. So they're going to be neutral, always neutral, because they have one stick, count it once, 1 minus 1 is 0, right? So hydrogen valence number is 1 minus 1 bond. So let's ignore hydrogen, just look at everybody else. So look at sulfur. So let's start here. The valence number of sulfur is just the same as oxygen. Its valence number is 6 minus, now how many sticks? There's 3 bonds, plus a lone pair, 5. So 6 minus 5 equals plus 1. So sulfur is plus 1. So there are 3 bonds, 3 sticks, and a lone pair. Look at oxygen. Valence number of oxygen is 6. I'll do it in blue. 6 minus, it has a double bond, that's 2 sticks. So each bond represents 1 electron that it owns, even though there's 2 are in there. So there's 2 electrons for the 2 bonds. Plus it has 2 pairs, so that gives us 6 electrons, right? 4 plus 2 is 6. So the charge is 0. There's no formal charge. All right, carbon, there's a total of 4 bonds around it, 4 sticks, 4 lines. So that's 4. Valence number is 4, so 4 minus 4, 0, right? Nitrogen, valence number is 5. All I'm doing is going up to my periodic table. I'm saying, okay, nitrogen valence number is 5. And so 5 minus, it's got 3 bonds, 3 sticks around it. So that's 3 electrons that it owns, plus a lone pair. And so 0. 5 minus 5. 4 minus 4. 4 minus 4. Okay, what about this nitrogen? This nitrogen has a double bond, so that's 2 sticks, and then a bond to the left makes 3. And then a lone pair makes 5. So 5 minus 5. So it's 0. See that? Something quick. Whatever you do for formal charge, make sure it's quick. All right. Nitrogen here is valence number 5 minus, it has a double bond and 2 single bonds. So 4 sticks around it. So 5 minus 4 equals plus 1. This is a positive charge. And there you have it. We just knocked out every single atom here. And that's how we do formal charge. Okay. Now, you might have noticed something, and you might have asked yourself a question. You might say, hey, this is great, but I noticed in my book or in class or my workshop that they don't show me the lone pairs. So how do I know when to put lone pairs in? That's the next part. Okay, so let's do that now. So how do you determine if an atom has non-bonding electrons? Remember, non-bonding electrons means either lone pairs or radical electron on the atom, but it's not bonded to anybody, right? So that's owned by the atom, right? That's the dots of the dots and sticks. So how do we figure it out? Well, this is a little tricky at times because there are certain things that violate our rule of octet, our outer shell of 8 electrons. So it kind of gets a little tricky, but here are the 3 things to consider. The first thing is you should consider how many electrons are required for the atom to have a filled outer shell. That's the first thing that I want you to recognize. Most atoms that we deal with need 8 electrons. There are exceptions to this rule. So for example, hydrogen only has an s orbital, 1s. It only needs 2 electrons. So 1 bond gives it 2 electrons. And so it only needs to have 1 bond, okay? Or maximum of 2 electrons around it. Boron, on the other hand, now it could make 4 bonds. But if you look at boron, its group number is 3. Which means that in its outer shell it only has 3 electrons. So being that a covalent bond is where they has to contribute one of the electrons to make the bond, it can only make 3 bonds by itself. It turns out it could make a 4th bond, but that's something that's not done through an equal contribution. It's an unequal contribution. We'll come back to that soon. But for now, let's just consider boron, just like aluminum, are atoms that only make 3 bonds, usually make 3 bonds. Boron could make 4, and aluminum can make even more than 4 because it's got a d orbital. It's the 3rd period on the periodic table, so it could do a d. It has a d orbital. But at any rate, let me just make this clear. We're going to just assume that boron and aluminum, for the first approximation, makes 3 bonds. All right, so that's the second rule. Now, phosphorus, because it's on the 3rd row of the periodic table, 3rd period, it could make up to, it can exceed 8 electrons around it. It can go to 9 and 10 and more because it has a d orbital. Remember, there's s, p, and d. So s, you can get 2 electrons. P, you can get 6 because there's 3 p orbitals. But d, there's 5, right? So that's another 10. So you can have 18 electrons in theory if you have d orbitals. So the p, phosphorus, and sulfur, they can have 8 electrons around it, but it can have even more. So that's where it gets a little tricky. So you'll see what we do in a moment. The second point I'm making here is that we should just begin by assuming, other than boron and hydrogen, because they make less than 8 by themselves, that everybody's going to have 8 electrons around it, because it's just a standard place to begin. So you'll see how to apply this in a moment. Okay, so we should make the assumption, besides hydrogen and boron, that it has 8 electrons, including sulfur and phosphorus. Okay, even though we know it could have more than 8 electrons around it. All right, and the third thing is that whenever they draw structures on paper, they do not have to show you lone pairs. That's why we're doing this whole section. So